So let's begin the program. I invite Professor Arvind sir to introduce our speaker.
So good afternoon, all of you. I welcome you all to this special lecture to be given by Professor Umapathy. As some of the senior students and faculty and staff would know, in general, before all our faculty superannuate, we have a symposium followed by felicitation. But we thought we'll try something different, thanks to the suggestion of Professor Umapathy himself. He's going to give a talk. You can see the title, the last lecture. He will tell more about this. As this is a special lecture to be given by Professor Umapathy, I thought I will give a formal introduction, because most of our faculty and old students and staff know about him. But let me give a formal introduction to him. I want all the students to listen to this. Umapathy did his BSc from Kongunadu Arts College of Arts and Science, and then he went to PSG Tech to do his masters. After that, he went to New Zealand, then did his PhD at University of Otago, following which he went to the Rutherford Appleton Lab and University of Cork for postdoc. He had a long postdoctoral experience and joined IPC department in 1990, those days as a lecturer. He rose through the ranks, eventually became professor and chair of this department, before he was appointed as the director of Indian Staff Science Education and Research. He has been a visiting faculty in Kanagawa Academy of Science, University of Groningen, Institute of Molecular Science, Tokyo, Imperial College, Hay and Nottingham University. Umapathy has been decorated well, starting from, in fact, I joined here in 1997. The year after I joined, Umapathy got the Swarna Jayanthi prize, which was given to young scientists. Later, he got the V Raman Award given by Karnataka State. Then he won the Bhatnagar. Then he got the J.C. Bose Fellow. He's a fellow of all the academies, and he has been fellow of Royal Society of Chemistry and many other. He has a Wikipedia page, so you can check out all of this. Now I invite Professor Umapathy to give the last lecture, Research Progress and Life Experiences.
Okay, so is it working now? Can you hear me? Okay. All right, so thank you very much, Arvind, and it's a pleasure to be here today. I'm not acting here, you can switch this off. Video and live streaming. Okay, I see. One at least you can switch off, it's too bright. Yeah, I've not got trained for acting yet, so too much light. So thank you very much. Actually, so I'm going to share the last 32, 33 years of experience in about 45, 50 minutes, and I hope you enjoy the lecture. So every time when many people who met me after seeing this notice of the last lecture, they kept asking, this is not the way to put a title, and some of my close friends said, it's very, doesn't sound too good, and all that. So I should tell you, this is nothing new. This happens all over the world. It's in MIT, it's in Harvard, in many places around the world. People, before they retire, they share their experiences, basically to the community, and therefore people can decide about their experience. And so, if you go to YouTube, you will see large number of lectures, people sharing their experiences, so that young faculty, students learn from their 30, 40 years of service in academia. So I'm going to talk about my group first. The group I have been working with in all kinds of areas, starting from, we use laser spectroscopy as a basic component and do computation and simulations. And using that, we apply this technology in 3 different areas: physics, chemistry, and biology. So as you can see, I've had students from physics, electrical communication engineering, biomedical engineering, biotechnology, biochemistry, chemistry. So diversity has always been extremely useful in the lab, because somebody who is extremely comfortable with the computers were able to help students who need to learn. Somebody who are engineers who had difficulty understanding chemistry or physics was able to talk to the students. So that actually added value to the research quality of our group. So today's talk, I'm just going to split it into 3 components, but the first component is going to be mostly 40 minutes, 45 minutes probably, and the other 2 will be 5 minutes each. In the first component, I'll tell you, we start with extremely basic sciences, and then we go into, some echo is coming, go into some applied aspects of research that we have done. Now what happens is, when you start looking at basic research, one of the biggest things that the whole world is looking at, if I make a molecule, what will it do? Can I make it conducting? Can I make it reactive to make a product that is important for the society? So every time you have a chemical structure, you're always trying to make. That's what everybody does, whether it is synthesis, whether it is physical chemistry. So in order to do that, you need to understand, at the atomic level understanding, of how these molecules react. And if you, for example, I've given you some example here. If you look at this is basically a molecule surrounded by solvents. So when you put energy into this molecule, the molecule starts reacting and start moving around, and therefore energy gets distributed, a reaction gets started. For example, this one is another example. I may not talk about it today, but I'll just show you a cancer cell that looks like this. Over a period of time, because of the way chemicals migrate within the cancer cell, they turn into a shape like this, which is called the spindle-like shape. When it forms, then it becomes invasive cancer. So one of the things we have done and demonstrated is that doctors can look at something like this only when the shape changes, what's called morphological changes. But what we can do from a chemical analysis, when the nucleus starts moving, when the protein concentration increases or lipid increases, we know that now it's going to become a spindle cell. So you can start taking action about removing it as soon as possible before the cancer starts moving into other parts of the body. So that's the kind of advantages you get by looking at chemical structures. And this, of course, I'm not sure many of you know, this is basically contrabands, people smuggling. So one of the things people want to do is, can we actually look at what is inside without having to open it? Because we don't know what is inside, what kind of chemical is. So these are the kind of problems that we have broadly addressed in my lab. Now for me, a chemical reaction is like setting up gears. How gears are allowing, how they transfer energy, how they transfer function, from first gear to fourth gear you're going, or even in any other component. So what matters in science, what matters in physics, chemistry, and biology is 3 major components: energy, time, and space, right? In every function in this world, including human relationship, these factors actually make a difference: energy, time, and space. Now, if you look at a gear system, the rate at which each gear moves, the speed in which they are moving, that is rotation per second, has to match with the next gear. Therefore, they can attach with each other and transfer the energy, and then transfer the function of moving in one direction or the other direction. And similarly, space, right? The size of the gear that you have in terms of spatial structure must be approximately correct enough so that you can lock in and transfer energy. And energy is basically the voltage that you give for the motor to start spinning. Now, this is actually true for electron and electron shifting, electron transfer, whether it is intramolecular or in a bond formation or bond breaking, trying to make a new molecule. So how is that related to chemistry? If you look at time, when you put energy into it, there are many states in which the energy is flowing. The energy can be electronic, energy can be heat, energy can be electrochemical, or energy can be by photons. once if you go to an excited state, then you need to understand instantaneously starts what's happening. How does the energy flows into the rest of the molecule? How come only that bond is breaking? Or how come the structure is rotating to create another molecule? So all that can be seen. They have a time dependence. The space in the interaction, for example, if you're in a solvent, if there are two different chemicals, they have to approach each other and make sure that the energy is the same when they're approaching, and the orientation of the bonds are sufficiently in the same direction, therefore they can interact and break or form a new bond. And the energy, in order to create all that, you have to give energy. In our case, we give photon energy. So you excite with light, so you add some energy. We can do it by heat, you can do it by other ways. So that's the chemistry and physics of these chemical processes. As I said, energy can be either light, heat, or electrical. The time process has to be from instantaneous to a product formation. And space is basically structural reorganization. You might have studied when you talk about how the molecules change, the molecules rotate. They rotate in a way that they can attach with each other to transfer energy. No energy can be transferred without two systems being at the same level in terms of spatial coordinate, in terms of time coordinate, in terms of energy coordinate. Unless these three are joining together, no reaction will ever happen. And that's what we are trying to say here. Right, so let's look at if I put energy into it, right? So you can see as soon as a photon is kicked, the electron goes up, then you create an excited state. Then that excited state can actually do lots of things. I'll show you. It can actually go to another state. Now each of the potential, so this is your bond length as well, because this collocation can be a bond length. If you go to another potential, it's a different bond. You go to another bond, so the bond can go finally to a product state. So the reactants can actually shift from one bond to the other, therefore it forms the final product state. So we would like to learn about the molecular structure. So each of the potential energy is one bond. If there is 5 bonds, 6 bonds, you will actually see 5 different structures. So what happens at different times, right? So we know that, the length of in a day and time, so I'm just putting some time scales. Now if you look at what happens in the molecular structure, motion of an electron in an orbit is about attoseconds. So unless you're looking at a helium atom or a hydrogen atom interacting in the gas phase, attosecond has no relevance to proper molecular chemistry. When you go to more than 2 atoms, you are out of control because the electron-electron correlation is too large, the density of electron is too large, nothing you can see in attosecond. But then when you go to further time scales, you start seeing the molecular aspects of the system. And you will see molecular vibrations, you will see molecular rotations. You can also see solvation, that is very important. Because the solvents actually give energy to the vibration itself. But we normally call it inhomogeneous broadening. In the past, people thought that it is a macromolecular property. You can see now that there are microscopic properties can interact to lead to a product. I'll show you an example. So that's what we try to do. So when we are trying to understand instantaneous processes from femtosecond time scale, because you can see the vibration. So for example, a CH vibration, which is about 3000 wave numbers, that is equivalent to about 3 femtoseconds, which means that once if a OH vibrate once, that takes about 3 femtoseconds. So if it is a CC single bond, which is about 1000 wave numbers, will be about 10 femtoseconds. So like that, by bond-specific time scales, you can monitor how the bonds move, how it rotates, and that's what we try to do. So this is what I meant by different electronic state. For example, you have different vibrational modes or different vibrations. If there are 5 vibrations, you'll have 5 different buckets, but they're all interacting with each other. So if you see what happens next, as soon as you put the electron up in the air, then they start interacting in the various vibrations in the excited state. Some of them go to different vibrational energy and then they can break the bond, or this one can come back as fluorescence and then that stay in the ground state. And you can also form a product state if you wanted to. And that's what you do. You decide how it works, right? So you can capture this electron. This is what we call phase space experiments. From this point to this point by watching how the phase of the light that is changing with respect to time. So we do 2 kinds of experiments. If you want to monitor a chemical process in time scale, you can do what is called a frequency resolved experiment or a time resolved experiment. So in the frequency resolved case, as you can see, the frequency resolved is related to the phase space, how you push the electron up with the photon. It has the same phase as the ground state. As it evolves, because of this interaction between the bonds or between various electronic states, the electronic phase becomes dephasing. It removes the phase from the system. And therefore, the dephasing time is about 100 femtosecond. So what we can do is, by looking at very closely this phase space, we can actually find out what happens to the vibration between 0 and 100 femtosecond. The time-resolved Raman, where we can look at, for example, how vibrations change from 100 femtosecond to microsecond and nanosecond onwards to days. And people have studied that, and many of you do it in stop flow experiments in beyond microseconds. So this is one example of a frequency resolved. When you say frequency resolved, what does it mean? So you have an absorption spectrum. Different frequencies in the absorption spectrum leads to different energies. Now when you go to different energies, as I showed you earlier, the energy can migrate to different vibrational modes depending on how it is coupled with each other. So by describing the electronic phase, we can calculate what is the kind of displacement. So this is what we call displacement. So you have ground state nuclear distance and the excited state nuclear distance. By watching the electronic phase, electron moving from here to this side, you can see there is a bond distance either increasing or getting shorter. By monitoring, you can say how it moves from one direction to the other. So this is what I meant by that. So what we do is we can do a simulation. We know the vibrational wave function here, and we know what we are creating. And because of the transition moment, you can actually calculate these wave functions and convert them into a Raman spectrum. And that can actually give you information, time-dependent change in the bond structure with respect to time. So I'm going to show you one example of something like that. Is there a time? 17, okay. I'm not sure I'm going too fast. Okay, so for example, this system I studied, this was studied in 93, 94. One of the reasons was that azobenzene derivatives were used in compact discs. One of the problems that people had was when you're doing compact disc, the rate at which you read information is important, or writing and reading, right? The writing is that cis is by 0, trans is 1. So if you expose light to 0, it switches to 1. So you can actually build a binary-based compact disc with molecules. Now, at those times, the rate at which you can read information was very challenging. So people were all worried about how rate can you switch. You know, when you go from cis to trans, what is the rate of transition? That was the problem. Now, there are two routes it can take. One is what is called the rotational state, which means that this double bond actually breaks into a single bond, and then this can rotate, therefore it can come here. The other option is in this case where you have a lone pair of electron, therefore it can do an inversion, which is if you excite the n electron into a pi star orbital, then it can switch, which means the double bond size will not change. So these are the two options, but people were not sure how it happens. So then we decided, why don't we look at that? And that's what we did. We actually changed the wavelength. As I said, we scan through the whole thing. These are the Raman spectra at different wavelengths. Then we do the simulation, convert them into some numbers and time. You can see at 5 femtosecond, the NN bond gets compressed, right? Which means that the NN double bond becomes smaller. When we say negative, that means it's compressing, and CN bond is stretching. And as you increase, you can see CN bond stretches, and 30 femtosecond it compresses more. And the RCC bond exactly the same. So you can now build, I'm just giving you 3 or 4 papers into 4 slides. So there are papers published on this in detail. You are welcome to look at them. And so what we can say now, when you are doing excitation in the visible, because that's what you use for writing and reading with 630, 500 nanometers, what they do is that this is, because pi star is somewhere around 350 or below 300. And therefore then that the excitation doesn't help. You can see the reason it is slow is because this excitation happens here. We see the NN bond continues to be a double bond, gets smaller, and this gets longer as a single bond, and therefore inversion happens. So we can show that within the first 100 femtosecond how the structural change is occurring in this case. Now we'll go to the time-resolved experiment, which is actually the real-time femtosecond experiment where we watch in real time. the questions in a chemical reaction you always ask is how fast it is going, why is it going in one particular direction, and what happens to the energy I put in. I put large amount of energy, but that seems too much. There is always this question we ask to the students is that if you put so much energy in a bond, it should break because you cross the dissociation threshold, but it doesn't, right? That is because the rate at which the energy flows is faster than the bond can break. And that's the reason why you don't break bonds. And therefore, what happens to the energy? Where does it go? Which vibration do they take? And of course, the next question is hemoglobin or myoglobin. It's all surrounded by proteins. Or if you look at reactions in solvents, this is something always puzzled me even during my bachelor's degree. My organic chemistry professor says that it is 90% yield. You ask him why only in this solvent, he said that's all empirical experiments. So these questions cannot be answered except to say a macromolecular answers like dielectric constant, polarizability. But the bottom line is, does that mean that solvents interact at the diffusion level, nanosecond? But in femtosecond timescales, solvents cannot even move. So where does the energy come from, or how does the energy get sorted out? And therefore, what is the role of the environment in controlling a reaction? So I'm going to show you one example of how solvents actually can control, and therefore how we can understand atomic level microscopic response of a system. So this is the lab we built up. When you want to do femtosecond Raman, this is not an instrument you can buy. You buy lasers, you buy spectrometers, you buy optics, lenses. This is what you see. You see these filters, the detectors separately, all these are separate. And then we build a lab, right? And that's what we did. And so what we do is, in this case, we are trying to do by bringing laser beams of different colors, and they're all made in different ways. And you have 3 colors now. One is that this is your red color, and this is your white color, this is your blue color, UV pulse. So we bring all the 3 pulses at 0 time, right? Light travels at 300 millimeter in 1 nanosecond. So if you go to 1 picosecond, we are talking about 300 micron. In 1 femtosecond, we are talking about 3 micron. So if you make a mistake of alignment of 3 microns, 3 beams will not come. So this is what is exciting when you actually try to do experiments at these time scales, because you are as fast as the vibrations happen, and we do that. So the problem I'm going to show you is another isomerization case, because I thought better to take simple molecules. We have much large number of papers we have published in many systems. I'm taking the simplest system so that it's easy to communicate. So stilbene going to cis-stilbene is started in 1981 and still being studied by people because it is a very complex process. Although in the time scale I'm talking about is femtosecond, not in a short time scale. So what the people found is the rate of isomerization in liquid is 20 times faster than gas phase. So similarly, if we look at the lifetime of the excited state, it is 30 femtosecond in acetonitrile, 100 in non-aid. So it's solvent dependent also. Not only that liquid is faster, but also in smaller solvents, like fast solvents like acetonitrile, it is 30. In a very slow solvent, it is 100 femtosecond. So people realize that solvent is doing something to this. So we will look at what is happening. So we recorded the spectrum at, let's say, 100 femtosecond, 200, all that of the excited state, and then we tried to see what is happening, and we saw oscillation of the CC double bond. Then we convert this oscillation into frequency. It's basically Fourier transformation of the information into frequency, and then we see that the frequency that is coming in here, which is actually at the oscillation of the CC double bond, then what is this is it? And so we found out, so this is just a summary of what I just told you, dephasing time and the oscillation. And what we found out, this is actually is the torsion. So when you're trying to rotate, it is interacting with the CC bond. That means acetonitrile is accelerating this torsion. This torsion couples with the CC double bond, so isomerization gets faster. And that's what we learned. And what you see here, you have not only torsional coordinate, but you also have the Frank-Condon excited state, which is the solvation coordinate here. Those 3 coordinates combine and push it to go faster. So that is why in a very simple load, high polarity, but highly polarizable in a short time. So acetonitrile solvation time is 80 femtosecond. If you go to butane on trial, it actually takes 400 femtoseconds. So the solvation, because the solvent rotates quickly, and so it can push the reaction. And that's the reason when some solvents are favorable for some chemical reactions. So now I'm going to take some examples of biophotonics. And the idea is how we can apply laser spectroscopy to biology and medicine. Right? So we do all kinds of work. We start with basic research. We also do applied research. And we have worked on biopsies, tissues, body fluids, and also model systems. Many of the life-threatening diseases cannot be studied using humans, or what's called lifetime-dependent diseases. So we have to use models like mice or Drosophila, and then you look at what happens and then go back to the hospital and compare with the patient samples. Because Drosophila, for example, 80% genome of Drosophila is the same as human genomes. And therefore, it's easy to monitor the chemical changes corresponds to them as much as a human changes is the same as what happens to animals. So what have we done in our lab? We have done tissue studies, for example. We have done drug-cell interactions. I'll show you one example. We have done liver injury using paracetamol, which is acetaminophen. We have studied sepsis. I'll show you an example. We have also studied nerve injury and muscles, bacteria. Muscles we have done with Drosophila. We have done TB bacteria. We also did lab of SIP and of course diffuse wave. But I'm going to show you only 2 examples because of the time. When you're trying to do this, one of the things to understand is how complex is biology, why Raman has not been penetrating biological area. There are 2 issues. One is getting a signal out of water, because water is a very weak scatterer. It doesn't give you enough signal, so you can't measure the signal of water. Then what happens, biology looks very, very impressive because infrared cannot be used to study chemical structures in medicine. Therefore, Raman is the most ideal. But then when you look at Raman, it starts burning the sample, right? Because you're using lasers, power density goes up, then the experiment gets difficult. So that was one problem with this. The second problem is, how deep can you go in a tissue? What can you learn from a human body when the light penetrates into the system? So these are all basic ideas have been done. This is called, if you go and see, there is something called the tissues are called the turbid media by people who are working in electrical communication engineering. They use optical coherent tomography, OCT. You might have done echo studies for heart. These are all done by basically sending acoustic signals, looking at the reflections and measuring the changes that happens in your tissue. But the light tissues have a different kind of penetration because you're talking about now chemical structures. You want to have it at a high resolution. So the basic idea is that we want a technology which can give you more than single solution. If you look at many chemicals, you can see what are the possible changes that are happening in multiplying capacity. Right now, doctors can only look at a micrometer size, right? They only look at through microscope. The best they can do is micron and above, nothing below. But if you take a cell, it's about 3 to 4 microns. And the nucleus is only about 1 or 2 microns or even less. If you want to understand the nucleic acids in the nucleus, they cannot see. They can only see the shape. So what matters is to them is morphology. So if today's doctors make decisions based on 2 things. One is your symptoms that you describe to them. If you don't tell them what is wrong with you, they can't tell you what is wrong with you either. And if you go tell them I have a headache and these are the associated aspects, they can tell you, oh, it must be related to this. The second thing they do is that ask you to go and do some various kinds of tests, right? All the tests you do, your MRI, CAT scan, PET scan, OCT, all of them give you information on density and penetration depth. So it doesn't tell you any chemical information. The only chemical information they can learn is what they do a blood test or urine test or test that is done in the biomedical lab or bioanalytical lab. And so there is only few of them that they can do. So we were then thinking, what are the challenges today? First of all, recording Raman spectra. So we know that biology is complex. In a cell, you have proteins, you have RNA, you have DNA, you have lipids, you have carotenoids. So we need to be able to delineate all of them. So these are all, for example, since 1970s, large number of people have been working on trying to understand what is the structure of a cell, what is the structure of protein, what is the structure of RNA. Well, how do you understand a Raman spectra of an RNA versus DNA? All that had been done, so we don't have to repeat all that. So which means we can use that data to understand what is happening in the system. And then we need to analyze data, because now you're not talking about single data. If you're talking about patient data, you're talking about 300, 500, and each patient will get 20 or 30 spectra. We are talking about thousands of data. So in the 2012 onwards, we were doing a lot of statistical analysis and came up with some reasonable ideas of how to do with univariate data analysis and multivariate data analysis. These two papers I'm showing here is one of the well-cited papers of ours, where we demonstrated that it is possible to do good data statistical analysis to get information which is very close to diagnosis. And so these papers are describing what are the mechanisms, methods by which you can do data analysis. So I'm going to show you one example of an extremely basic research. One of the questions was that if you have a brain cancer, if a patient has a brain cancer, the drug that they use is called HDAC inhibitors, which basically means, which is what is called HDAC-I, right, which is histone deacetylase inhibitors. Now, what we wanted to see, because we can see the cells, the brain cancer cells, we can see what are the changes that happens when the drugs start interacting with them. And what is the process of this? So you have, what you can see here is that you have a histone core, which is the histone protein, and the DNA is surrounded by it. There are another set of histones, actually, another protein combines them. So there are different kinds of proteins. You can see here histone, where various names are there. But what we are trying to do, we are trying this histone basically does acetylation and deacetylation. If this balance is not maintained, you get cancer. So deacetylation inhibitor is that you reduce the deacetylation, increase acetylation, therefore you can kill the cells. So that is the reason why they give HDAC inhibitors. But there are 10 different types of HDAC inhibitors, and for some patients, some HDAC inhibitor works. For some patients, it doesn't work. So my friend with Kumar Somasundaram, we are working with him. First of all, we have to identify what is the biomarkers, for example, to know it is working or not. So by looking at the histone structure and look at this extra CH3 group, we can say that it is working or not. That is, acetylation is happening or not, we can mention. We then decided to go and say, let's look at all the HDAC inhibitors. What we found was, we ended up seeing some more information. For example, valproic acid, sorbitol, apicidine, temozolomide, ceritinol, all different kinds of drugs. And these are the solvents we use, and of course the control. So when we did that, we found that in addition to acetylation, we also found propionylation. So when I told Kumar, look, it looks like we are seeing propionylation, he said impossible, because there is no record in biomedical chemistry that the propionylation can happen. I said, but we are observing. So we repeated the experiment. And then he said, okay, let me double check. He went and then got some enzymes to do the propionylation of the glial cells, came back and confirmed it does have propionylation. So it's one way of where spectroscopy then can guide biomedicine, where you can actually see propionylation was happening. Therefore, now they are looking at whether propionylation can be stopped. Maybe does it help the cancer cells or not. But other important interesting thing we also did, we took 5 different cell lines, incubated with 2 different drugs, and we demonstrated we can actually monitor in 24 hours which drug is more suitable for which patient. So you take the cells and then incubate with the drug and see which is the most efficient HDAC inhibitor. So this is basically a personalized medicine for people who cannot try multiple drugs. Immediately you can start treating them with this kind of stuff. And so this is the assay I told you that Kumar did in his lab, confirmed that what we are seeing here is also confirmed biologically. So this is what I meant by, we can do drug screening, we can do cell line screening by fast methods of Raman. The other example I want to show you is that, all of us have experienced in the last 4 or 5 years, I'm just showing you most recent result, is that viral breaks. You see you have COVID-19, yesterday there was Nipah cases in Kerala, dengue is very much happening in Bangalore, and of course seasonal flu. And this diagnostics is a big problem when the number of cases go up. It's easy when the numbers are very small, And so what we decided to do was we started looking at it to see what are the technology available today. The most comfortable confirmation technology available is RT-PCR, which take typically 2 to 3 hours per sample, and you need to know how to do them. Otherwise, you can't get good results. So you need to be an expert. Plus, also it's expensive. The RT-PCR instruments are very expensive. For a large-scale screening, it has not been very comfortable. That's COVID, for example. We did a lot of these. The other two tests we saw is what is called serological test or the point of care device. Both depends on the antibody concentration in your sample. Therefore, if the concentration is low, then the direction becomes very difficult. So what we decided to do, we wanted to use Raman. And of course, a friend of mine, Dr. Sarman Singh, who was the director of AIIMS Bhopal, he said, can we do something? I said, okay. One of the reasons is when patients arrive at a hospital, you need to make a decision whether it is infectious symptom or a non-infectious symptom. So then, during COVID time, there is a lot of infrastructure being wasted. Things like, uniforms, masks, and various other things. So can we find a faster? So we said, why don't we try? And that's what we did. Symptoms may be very similar, but the proper decision of whether it is COVID or flu or dengue could be something else. So that's what we wanted to do using this technique. And of course, in order to double check viral infections can be seen, we also have tried dengue. So idea is that we take a blood from the patient, and then we look at the plasma. Plasma contains various components in the body, and they all help. This, fibrinogen helps blood clotting. Immunoglobulin fights the infection, and it transports material and maintains the pH. And of course, the proteins are the ones which change a lot during the infection period. So we tried to see, we can chemically identify the various peaks, what it belongs to, which chemical component it is, and therefore we can monitor them much more closely. So we use now AI. So since 2017 onwards, we started using artificial intelligence as a way to analyze data. Since the patient data is in large tens of thousands of data, simple statistics sometimes doesn't help. You get 70-80% accuracy, but if you go to AI, you can get close to 98-99% accuracy. And that's what we have done in the last 4 or 5 years. And so what we do is we actually take patients, a set of a test, and then the disease test, and then we separate them into various components. And the generative artificial network, you must be hearing about this quite a lot. The generative AI is what is revolutionizing the world today. Everywhere people are using generative AI. And that's what we also did. And so we try to look at the final result. I'll show you the confirmation here. What we could do is, using Raman, we could actually see 100% COVID, 100% dengue. In the flu case, it was 93%. Some of them went into control. But we can definitely identify COVID and dengue, which is actually going into our new technology, which is coming up. So I want to share with you about some of the projects we did as a consultant. I started consulting with companies in 1994, and last 30 years I've been still consulting with various companies. HLRC, which is the Hindustan Liver Research Center, now it is called Unilever Research Center. I've been advising them. We used to work on tea. I didn't know anything about tea until I started advising them. And the 3 roses that you get in Bangalore and the 3 roses get in Lucknow are 2 different 3 roses. If you want, you can buy them and have a look at them. The reason I will tell you, in the south, people like flavor. In the north, they like color and flavor. And therefore, the kind of tea that is used, packaged for the north versus south, and it's also region, west, east, and also, I'm not going into details. So one of the things we tried to do was, spectroscopy, of course, color. So, I was advising them to how to do the measurements, how to calculate, how to get things done so that you get the proper color, plus also taste, and I can tell you, if you want to brew a fantastic cup of tea, there is a connoisseur's technique. It is called, you have to heat the water. You have to put a thermometer in the hot water and wait until it becomes 70 degrees. Put your tea bags or tea, you stir it, wait for something like 90 seconds, and then take it out, right? If you stay any longer than 90 seconds, there is something called catechol, which actually dissolve tea into water, and that's what gives you taste. But catechol have different molecular weights. So larger, high molecular weight catechol gives you bitterness. And therefore, if you leave it too long, high molecular weight catechols actually go into water, and therefore you see bitter taste that comes out if you're drinking tea. So that's one example. The other did I worked with, I don't know how many of you recognize this aircraft. You know what this aircraft is? It's a 787, Boeing. It's a project we did. So they were using what is called the carbon composite. So right now, most of the aircrafts have almost 60–70% is all aluminum composites of high stress, handleable, high friction handleable, high light handleable, all that. And when we started the work, they saw a paper on depth resolution in Boeing in the US. So I got an email from them saying, look, we saw your paper. We have a problem. We want to know whether you can handle it. I said, okay. So then we communicated. And then the team from Washington, Seattle, the Boeing Center came here. And we had a meeting for 3 days. And we discussed what their problems are. The problem is that when you have carbon composite, you have friction, you have exposure to extreme UV, you have exposure to temperature -45 at 40,000 feet, and then you land in Rajasthan at +40. So the material has to withstand that. So they wanted to understand the integrity, and that's what we did. So we did the project for them, and of course the agreement was that whatever I do cannot be discussed anywhere outside the details, plus all the reports and everything, they have taken it with themselves, with an agreement that we will not raise any claims or anything like that. So I can't give you more details, but then we did some work on Shell Corporation about 5–6 years ago. How to calculate, how to monitor the amount of selenium that comes out of the spent water. So when they pump out oil, it also comes out with water coming out. When the water comes out, then they have to measure the selenium. There's an international standard of how much selenium is allowed to come out before it can go into public. And therefore, they have to reprocess the water to make sure the selenium concentration is low. So we did a project. I still work with, interact with the ITC guys. So this shampoo, I don't know how many of you have used. There are many more shampoos and soaps of Vival, including transparents and all that. And so I was part of that committee. Actually, I was the chairman of the committee to certify that all their consumer tests were valid, because I was the chairman of their ethical consumer committee, plus also advising on how to measure the various body responses to toxic chemicals and how do we do that. So that's the kind of consultants I did. So it's all exciting stuff. When you do that, you learn a lot. You learn a lot about focusing and delivering results, trying to define a research problem, how to define timescales, how to make sure you deliver what you want. Then we went into started looking at their applications. You know, when you start looking at applications, it has enormous applications, Raman, as you can see, starting from medicine, food processing, forensic science, geology, cosmetics. So the number of questions were remaining. You know, many of these, you know, right now microscopes, spectrometers, you have to put a small sample under a microscope, look for signals. Here you can't keep looking. They're all composites, or they're all packed. So what are the challenges if you want to apply it to this? So this we started in 2008, 2009. So what are the challenges today at that time, 2008 to 2012, are the following is the challenge. If you want to understand chemical samples in real life, in terms of depth resolution, you know, there is a need for going up to beyond 5, 10 millimeter or, you know, 2 centimeter. Right now, most people are able to look at Raman maybe up to 1 centimeter. So when we decided how do we go to 10 centimeter, right? And then the other problem is resolution. If you look at spatial resolution, people can go to 10 millimeter, 1 millimeter and all that. But when you go down below micron to hundreds of nanometers, no, nothing is available. So what we want is on the y-axis, we want 100 nanometer. On the x-axis, we want 10 centimeter. That is the most ideal way to get Raman signals of the best samples that you can get. And that is where you can get chemical information and spatial information of these two. So that's where we went and developed this technique called UMARS. I think most of the faculty know because I've given a talk on this 7 years or 8 years ago. So how do you then start a problem like that, right? you only seen a light putting on a sample, measuring the scattering. But now I'm looking at 10 scattering and Raman scattering. Now Raman scattering is extremely weak. So move far away from the sample, less light you get back. So we had to think about how do I get light at 10 centimeter, right? So then we go into fundamental physics, right? Looking at electron-electron photon correlations, look at Rayleigh scattering. So if you look at, for example, you are getting these weather patterns on your mobile phone on weather, right? Where you see density of clouds and all that, they are all done by light, but they are using Rayleigh scattering. So when I looked at that, and I also have another friend who is working in London Imperial College Hospital. He developed a technique whereby he measured the level of oxygen in brain, in skull of babies using near-infrared light. And I was amazed and I said, God, he is penetrating 6-7 centimeter and looking at absorption differences. He is only measuring absorption. So we asked the question that if light can penetrate that far and show differences in absorption, then we must be able to measure the Raman scattering at the distance. But of course, we need to delineate from the other scattering. So we started understanding what is the basic principles of. So this is, for example, is what is called a turbid scattering media, which is a cloud or a tissue or a gel or anything which is turbid. And you put light, the light travels in different ways. There is something called, which is, ballistic photons. These photons go straight to the detector. Then there are other photons, which are what is called diffuse photons. There are snake-like photons. They all take different route. They all arrive at the detector at a later time. So then we said, oh, so that is possible. If you measure long enough at different location, you should be able to see the signal. So we went on to do some simulations. We then came up with this idea. Let's do one thing. I put light here. This light generates some Raman and some Rayleigh. The Rayleigh goes and hits another particle, generates some Raman and some Rayleigh. So you have multiple particle scattering at multiple times. So this is why you still universal multiple angle scattering, because Raman scattering is always measured for polarization reasons at 90 degree or 180 degree. By doing this, we said if you look at 360 degrees, we get not only major signals, but we also get, for example, larger signal to get. And that's what we wanted to get. Finally, you can calculate the amount of light, Raman light that comes out, and you should be able to predict. So we did a Monte Carlo simulation, of course, rewriting all the Monte Carlo equations for Raman scattering, and we demonstrated that it is possible to get signals. And this is the idea. So you have a system where you put light all over and then measure signals in all directions in 365 days, 365 directions, 360 directions, you in a ball. So by measuring signals in all directions, you will get much better signal than any of these. Now these are all theory, right? So how do you prove in experiment? So we decided, let's take a system like this. Let's say a cuvette, which are 3 cuvettes. In the first part of the cuvette, I add 1 chemical. This is second chemical, and that is the third chemical. I put light here. I'm wondering whether will I get a signal of the third chemical or not, right? If I'm right, if the light is traveling through and giving scattered light, then I should get signal from the third part. So when we did that, this is what we did. So for example, we put a tube with 3 partitions. You have 1 chemical ammonium nitrate here. You had this light putting at the center, and then you have trans-stilbene, dichlorobenzene, all these solids, and then you put light here, and then we put detectors on the top separately, detector here and the detector here. We could see fantastic signal. What do you do next? Patent it. So that's what we did. Now that we know we can penetrate and go to long distances, we immediately patented it. Then we decided, ambitious. I always tell a joke about this. I was talking to Balram and I said, I want to buy some bottles, to do some experiment. He said, what bottles? I said, beer bottles. He said, beer bottles in Indian Institute of Science? No chance. I know you will drink it, so I will not permit. I said, no, I promise you I won't drink. Your accounts officer was stopping it. Then he said, okay, then I allow you to drink, allow you to buy the bottles, but Balram, I have to tell you something. I promise you I won't drink, but I can't promise my students won't drink. Then he said, no way, you cannot buy, it's not allowed. So then I had to spend my personal money. All of you should appreciate the fact that I spent 500 rupees in the cost of this nation's protection by being beer bottles. And you can see here, this is a brown bottle, this is a green bottle, and we can see what is inside without opening it. So I can tell you hydrogen peroxide inside, acetone inside, alcohol, whatever. And we can also do in PET bottles, we can do it envelopes, I've demonstrated all of them. And then we got more ambitious. We went and did a chicken tissue, which is about 12 centimeter long and about 5-6 centimeter diameter. We actually put a broad light, diffuse light on top, and then we actually scanned from top to bottom, and we regenerated the signal. And what you see here, this is it. So we can actually see what are the particle size which is hidden inside, what is the thickness, how big or how small it is. And that's the kind of thing that we can do. So this is the advantage. You can now apply it everywhere. So of course, the next thing to do is we did some work for DRDO. So this is a technology to detect explosives. The light comes out, it can see what is inside a bottle, if it is there or not. We made one more machine for DBEL, where we actually showed, you can look at, this is the sample holder. It's a touch screen. You can do a Raman of bacteria in small quantities, put them in, close the door, press the button, you'll get the spectrum and tell you what bacteria it is. And that's what we have done. So then we went to startup. Life is difficult. They started about 4 or 5 years ago. And of course, I put down here, now lack of time, I'm not going to discuss the details. If anybody's interested, I can tell you it was not a very pleasant experience. Some upstarter from IIM will come and say, tell me, sir, how much money can you make? He doesn't care about technology and all these. So what do? You say, yeah, smiling, yes, yes. So that Abhishek was also saying that if you want to do a startup, throw away your ego. Throw away your position as professor, scientist. You assume that you are some upstarters are trying to say, hey, please give me some money. I want to do some research. Because it's extremely difficult, because convincing people who don't understand depth of science that this has a future is not easy. But I'm glad to say I have managed to get 2 investors who have agreed to invest $2 million, and we are in the process of signing agreements and stuff. What are we going to do with this? This is the name of the company, Gyroid Photonics Innovations and Technologies Limited. Shortly, it's called Gyrofint, Safety and Health by Light. These are the verticals. We have health, where we do diseases of different kind. We do prognosis disease. It's called Gyromed, which does diamond, gem, silks, and counterfeits, pharma, and petrol. We do security, explosives. I will show you one technology to detect all these. And of course, we do consultancy for space or universities and other applications. So one example I'll show you is sepsis. Sepsis is a disease where 50% of people get killed in the ICU because of infection. And so what we do, we take the blood plasma and do the analysis. As you can see, we can predict almost 98% accuracy. And so this is the instrument which is now being used. We have done almost 800 samples. We have 98% accuracy. So this is going to go into market in another 6 months or 1 year, hopefully. So there are very other applications are there in medicine. We look at blood, sweat, CSF, and skin, of course, and other things, cell sorters and all that we can do. This is a technology you might see in the airport in a year or so when you're going to the airport. This one, for example, is being used for checked-in baggages. If somebody puts some chemicals inside the checked-in baggage, it goes to 4th floor and they will open it, and then they will use to see what is inside without opening your package, so that it doesn't get destroyed. And this one is for passenger, which is a cover with a door here. So you put the sample inside. If you're carrying a backpack, you're carrying some chemical or some powder or liquid in your bag, they will take it and put this and check whether it has got explosives, narcotics, or any other flammable liquids and all that. And so that's the other thing, technology which is going in. So some comments for young people. This is what we try to do. We realize that when you come to the institute, you're all guys who have just read textbooks, written exams. We convert you into somebody who can solve problems by knowing how to answer the questions or how to start the problems and all that. So one of the things that I always say, the 7 habits that you should have, is that you should understand the philosophy of research. The philosophy of research is not about adding a methyl group in place of ethyl group, right? So that is not innovation. That's not creativity. You need to understand what creative research means. What does innovation mean? Innovation means it has to be, nobody should have ever done that before. If you're going to take a molecule and say, okay, this is happening, so I will do something different, the heated zinc, I'll do copper, then you're not doing great reason, right? And that's not research. Okay, I always say that. And values, you have to be extremely honest, and you need to be committed to what you're trying to do, and you need to have a personality where you give information, you will get information. You can't be cunning and trying to be jealous by saying, if I teach my classmate, he will become better. That's impossible. They cannot become better, because if you are good, they will also be good. They will become good. You talk to them, they will talk to you. I always say this, in my lab there is no senior, junior. You can ask all my students. Because everyone has some strength that you can use others and benefit, right? You need to have motivation and perseverance. The biggest problem is that when you do research, if you are continuously successful for a year, you're not doing research, you're only doing practicals. So you should look back and say, my God, what am I doing? Research means you must have failures. If you don't have failures, you don't learn anything. When you learn something, that you have learned something that other people have not, right? You get better and better. And that is very important for young people. And the other thing is management of time. You can't keep playing all the time. You can't keep watching YouTube's lab. So you have to make a choice, right? You should watch YouTube. I'm not saying don't watch. But don't spend 50% of your time watching YouTube. 10% is fine. Right? But then you need to make sure that you mentally relax, come back to the lab or come back to concentrating. And communication, this is very least well understood. See, on the one hand, you want to become an international scientist. On the other hand, you think you don't want to speak English. That's not right, right? So this is an opportunity for you to learn and how to communicate. And you give 10 seminar, 20 seminar, you'll be surprised. By the time you give the 25th seminar, you'll be 1,000 times better than what you started with. And that you need to understand. Nothing wrong in learning. So that's something you have to do. Because internationally, if somebody cannot communicate with you, I can tell you your relationship with that person will become very minimal. They will stop talking to you, they will not interact, they will not call you again. All these will happen. It's also true for faculty. If you can't give a good talk, next conference, don't expect them to call you, because I have been in so many committees. These are all come up. They always say, okay, who should we call for the next meeting? Send names. So it's all circulating on email, right? Then they will say, oh no, last time he didn't give a good talk. Do we really need to call him? All the discussion will come up. So you need to make sure you communicate well. Success, you know how to handle it, right? If you're successful, you'll be the most humble. You'll be the most friendly. If you're arrogant, you think you're going to walk around with success, you're actually ready to fall, and there'll be nobody to catch you. Because nobody can be successful 365 days for 20, 30, 40 years. So there will be downs and up and down. But if you're nice, there are always enough people to help you to come back up again. And that is very important. This is for faculty, young faculty. I gave this talk in IISc Bhopal. This is on YouTube. You can go look at it, Navigating the Challenge of Building a Career in Academia. There are a lot of challenges which you probably don't realize. I also didn't realize when I started. The issues are the following. Your perception versus the perception of the person who is evaluating you. You think that, I'm in the most complicated area of research, so if I publish 2 papers, I should become a professor. But the professor who is evaluating you doesn't have a clue your area is complicated or not. He says, I want 15 papers, otherwise don't even discuss. This is true at the national level. This is true at the international level. Science has become extremely specialized. It's not easy for somebody to make a judgment on somebody else's performance. Right? Things are getting very difficult. And if you understand that, you know how to make a compromise, how to publish, when to publish, where to publish, and therefore how to communicate your publications. So then and the problem of choices of research problem. I've had people, I'm experienced what in Bhopal, even here, I say, what happened here? No paper for 3-4 years. I'm working on a really difficult problem. Difficult problem. How difficult can the problem be? If you're working for 4 years and if it is so difficult, it's not worth working on it. You have to deliver because you're working taxpayers' money. It's not free money. It's not your father's money. You say, oh, I take 4 years, I take 8 years. You cannot do that, right? So you have to remember that any time you do research on public money, you have to deliver, whether it is a student, faculty, professor, head of the department, director. As much as the faculty asks money to the head of the department, Head of the department gets asked money to the director. Director has to ask money to the ministry. Because I did that job. I tell the faculty, please remember, I also have to justify. And the guy, I can tell you, the finance guy in the ministry is a good friend. I speak to him very freely. He also says, sir, you don't think I'm just getting money. I need to go to Ministry of Finance and convince them for IISc we need to get funds. So he has to write a list of reports. He says, sir, can you please send me a one-page write-up why we should fund IISc? Because they are competing with IITs, NITs, IISc, all these central universities, right? So somebody who's sitting down has to release money to different institutions. There must be justification for another. So everything percolates down that way, right? So you need to understand. If you understand it, you will manage your finances well, your project funding, timing, everything well. So I have to thank all the people who gave me money, who worked with me, Kumar, Dipankar, Anu, Sigda, Upendra, Deepak, and Vani Santosh from Nimans, Geeta Mukherjee from Kidwai, and Sanjay Kulkarni from Ramaya. They all, very good friends. We disagreed, agreed, but we never lost respect for each other, and that is very important. These are my students. You can see they are always playing, having fun, and I'm going around working hard, giving lectures, right? I mean, it's not easy to stand in front of you. But anyway, I always believe that if you have a good team, you can play a very hard game, right? That's what, if you look at any kind of team in the world, most successful teams are the most successful team, are the best in their game. And of course, you can see, these are so many parties these guys have had. They never invite me to any of these parties, but they send me photos. And it's been an honor to be in the institute, and it's a pleasure to have given this talk. And thank you very much. Any questions? Yes.
What kind of intensities do you use for the incoming light?
No, because we diverse it, right? You can use 100 milliwatt, 200 milliwatt, but make sure that power per square centimeter doesn't exceed more than 100 microwatts.
Okay.
That's important.
So when you have the diffuse light one, so what is the typical intensity that is falling per square centimeter?
That's what I mean. It's few microwatts
Okay.
per square centimeter.
Okay.
But when you distribute such large volume, the average intensity comes out is very large.
Hello, sir. Good afternoon.
Yeah.
I am Shubham. I am a PhD student in the department. So, actually, it's a very little general question, or your opinion. Like, you have been in the department for so long time, and now you will not be participating in any activities, faculty meetings, and all. So, would you like to say anything as a suggestion for the department, how you would like to change anything, the way it functions?
No, so let me tell you something, right? I think some of you might have been there when I was the chairman of the department, of course, RNN, and of course there will be another chairman in 1st of August. See, everyone has their own style of leadership, okay? But the bottom line is simply, all of them are working towards the department getting better and better. Okay, that is the reality, right? The style of operations, method of approaching that, leading to that result could be very different, right? And I think for me, the most significant thing for a successful department is high quality faculty. Recruitment of faculty must be extremely good. That's number one. Maintaining the facilities that are available in the department, that is always functioning and protected and very fairly distributed, that everybody has access to it, right? And then number 3 is that attract the best brains as PhD students. Okay, we should not be waiting for students to come and say, okay, join. So I always tell young faculty to travel around the country, which I did. You can ask Ramakrishnan, Arunan, PK Das, when we were young, we used to go to small places and where there are 3-4 colleges together, they organize a meeting. We used to go give lectures. Because the idea is to motivate these small place people who are doing well to come and apply, right? So idea is that if you have very good quality students getting admitted with good facilities and good faculty, department will automatically do well. Okay.
Anyone else has any question or comment? If not, let's thank Professor Umapathy for a wonderful presentation.
Thank you.
Let's begin the felicitation ceremony. Now, I would like to invite Nanjappa sir and wife onto the stage for felicitation.
Now I would like to invite Professor Arunan to the stage for felicitation.
Now, I would like to invite Rupa ma'am for the felicitation. I would like to invite Ms. Aneshwa and Shaibalendu for presenting the T-shirt. The T-shirt is designed by Aneshwa.
Moving on to the felicitation speech, I would like to invite Professor Arunan sir. Stage.
So good afternoon again, everyone. We are here to felicitate the senior most staff in our department. Mr. Ranjappa joined our department more than 4 decades ago. He is really the senior most, more than all the faculty who are currently in service. He started as a project in aerospace, I think, and then moved to our department. He has been a pillar of our department. In fact, as I told you, he has a much longer history than all the faculty here. One thing I would like to mention about this, that some 5 years ago, the then divisional chair, Mr. P.K. Das, wrote a mail to all the chairs of the division asking us to suggest one person to take care of the new building. Of course, I couldn't think of anyone other than Nanjappa. I called him, I spoke to him, told him we have a very big responsibility. I would like you to be in the new building. And of course, in organic chemistry, unfortunately, they could not suggest anyone. And from SSU, Mr. Rajesh was identified. But Mr. Nanjappa took it as almost a big challenge, and more than the challenge, a very big responsibility. So he came into the building when there was nothing, no power, no water, everything was there. And he really took it upon himself to be the guardian of the building. And he was here almost all the time. Nanjappa, can you just show the T-shirt? I don't know if he saw it. So we thought we should really remember that. Because when he came into the building, there was nobody. Remember, water, power, lift. Anyone gets stuck in the lift, he is the one who is called. There is no power, he is the one who is called. If there is no water, he is the one who is called. So he was here almost 7 days, almost 24 hours. Anytime and all the time. So I must thank Aneshwa and Saibalendu for helping designing. Aneshwa came up with the design, suggesting the T-shirt basically reads Champion of Chemical Sciences Building. I think he fully deserves this. Thank you very much, Nanjappa. I know that I'm not trying to reduce the significance of whatever you have done in IPC before this last 5 years, but this has been extremely helpful, not just our department, but the whole division and of course the institute. As many of you know, Chemical Sciences Building was called New Chemical Sciences Building initially. We used to get mails saying that NCSB. And we were always getting confused with the NBCS. NCBS, yeah. But before we moved in, it was no longer new. So then it was decided we should remove new from the building name. As you can imagine, when we moved into the building, it was old and almost dilapidated. There are a lot of problems. But Nanjappa stood here as a pillar and ensured that everything is fine. Initially, I think from SSU, Vek Tiwari came, and then YPC, Virabhadrao's group came here. And even before that, we had the NMR installed in this building. So he has been here almost 5 years. I know he didn't take leave That's probably common for many of our students and faculties. But he did not take any leave, not only during the 5 days of the week, but also in the weekend. He was always available. We thank Nanjappa for that. And of course, that would not have been possible without his wife taking care of everything at home. So thank you very much, madam. You have almost given Nanjappa to the institute for 5 years. I know that. We really appreciate your help. Of course, Arunambi, I must mention his name because our department has been lucky in terms of the support staff, office staff, everything. When the divisional chair requested that I identify one person, of course, the other building needs someone to help also. So thankfully, we had Arunambi and Nanjappa. So I told Arunambi, you take care of the old building and let Nanjappa take care of the new building. And of course, it's an uneven load. Of course, in the old building, one may get bored and scared. But in the new building, it's always emergency. Every day is an emergency to handle here. And Nanjappa took care of it enormously well. Thank you very much, Nanjappa. Thank you all.
Now, I would like to invite Professor P.K. Dasa for the felicitation.
Good evening, everyone. And chairman actually asked me that I must speak. And of course, there are two persons who are superannuating today, or at least in this function, and they're superannuating at the end of the month. And I saw that a large number of people will be speaking, all right? And there is also another reason. Nanjappa was there, I think, by the time I joined the department, but Uma was not there. So in terms of seniority, Nanjappa is senior to both me and Uma, okay, in the department. So when I came, Nanjappa was also, he joined definitely earlier than me. And in those days, IPC, actually we were fortunate, unlike the younger people today. We had about 10 people who are looking after various things in the department. And most of them will not know when they come and when they go. And either somebody is chasing them or you are chasing them. And that was actually, but there are few you can always find in the department. 9 to 5, they'll be there. Nanjappa was one of them. Okay. Whether he's assigned to your lab, to your office, or whatever it is, if you go and ask Nanjappa, can you do this? Okay, he will say, okay, sir. And then, since Nanjappa was in the department, I came to know his brother also. He was also working in the account section. And I always needed, because, when you start your career, you need to know people in account schemes and so on. So, and his brother actually still works in this campus. I mean, if you know him. And his brother and another person, both of them are in accounts. They still take a walk in the institute, and I still say hi to them. And so then slowly I started knowing Nanjappa, his brother, and many other things, okay? But then later on, what happened, that Nanjappa was very sincere. So a lot of people will actually look for Nanjappa. They won't look for the other 9 probably, okay, for whatever reason, okay? And Nanjappa was getting a lot of work. Okay. But then we moved to this new building, as Professor Arunan mentioned. And after moving here, he became the key man of IPC. In fact, initially for the chemical sciences building, but then of IPC for sure. And he will be in a room sitting there with large number of keys. And I wouldn't know which those keys goes where, who they belong to, nothing. But Nanjappa has actually marked them. He will know which key will open. In fact, recently there was a very interesting incident. Now we have a pump house. And what happened that there was no water in the building, but there was water in the sump. And the pump has to be started, and there was a lock. And everybody else came, including the security who was supposed to have the key, they're looking for Nanjappa in the campus because Nanjappa knows where the key to that pump house is. So he really, strictly speaking, he is the key man of IPC. And so any of you don't have a duplicate key in your lab or office, please ask him before July 31st because after that, I don't think even the chairman can guarantee that he will know where the keys of any room is in this building. And I'm serious. And please take my advice that if you don't have a duplicate key, ask him, he may still be able to locate it, where it is. After that, you are at your own risk. Okay? So Nanjappa is that kind of a person. And people will call him in the evening, he will come. The fortunate or unfortunate thing is that he used to live in the campus, next to the Janata Bazaar. And he will come running because somebody is looking for a key and that has to be done. Okay? And Nanjappa, very, very sincere, and he actually loves the institute. And that's why he has been so dedicated for so many years, more than 4 decades, as Professor Arunan said. And, well, Nanjappa, we are all grateful to you for all your service that you have given to this institute and to the department. Well, initially you were in aerospace engineering, I guess. Okay, so to the departments, let me just modify the statement, but mostly to IPC, right? Right, I remember that I also came to, in 86, but I came later, and you came earlier, so you were there. So yeah, well, thank you very much, and I also thank her, because when Nanjappa was working in the department, she was suffering at home and trying to do some other things, okay? So, it's a wonderful team, and, see? So, no, but without him, no, IPC will not be able to function, and you'll see after July 31st how they suffer. And so, have a wonderful life, Nanjappa, and you, and have a very peaceful, happy, and long-lasting. Thank you very much.
Now I invite Professor Ramakrishnan to the stage for the felicitation speech.
Firstly, I think I'd like to add to what two of my colleagues have already mentioned. If he was there when Pushpendu joined, he certainly was there when I joined. So, I think when we all do science in our respective laboratories, we often forget how much the support system in the department actually enables us to do what we're doing. And of the supporting infrastructure that we have in the department, as Pushpendu said, we had a very large number of laboratory assistants, as they were called in the early days. And they would help us do many things, and so take the headache off many things. And we had a large number of them. And as Pushpendu said rightly, many of them we will be looking for. Once they are assigned to our labs, we have the responsibility of locating where they are. So this would be a big task. Often it would be easier to do what you have to rather than go and look around for the person to do it. And that we did many times too, depending on whom we had assigned to our labs. Their roles have changed. If you ask the previous generation, like Professor Krishnamurthy and Professor Krishnan, many of them used to actually be in the lab, distill solvents, and do a lot of things that were there. But by the time we came, that role had changed. And as Pushpendu mentioned, there were several in the department who are extremely dedicated. And Nanjappa is certainly one of them. It comes to our mind, he's always there and always willing to help for anything, whether it was his task or not, his assigned task or not. I mean, that's a characteristic that was very unique. Likewise, Arul Nambi was also of the same category, who would to whatever you ask him, and do it with a smile, not with a grudge. And I think these are very important pillars that we relied on heavily. And as both the chairman, Prof. Arunan, mentioned, in the process of moving here, I think Nanjappa has been a real pillar of strength for our efforts to move as smoothly as we could. And I think the role that he donned and sort of the seriousness with which he took that responsibility reflects the personality that Nanjappa really is. So I don't want to take too much time, but all I have to say is, Nanjappa, you've been a real pillar of strength, and I wish you a very joyful superannuation, post-superannuation life, healthy and joyful life. And Madam, I'd like to thank you very much for all the support you've given us indirectly by supporting Nanjappa to do what he had to do. So those few words, Nanjappa, thank you very much, and we owe a lot to your services as a department. Thank you.
Now the stage is open for the audience. If someone wants to talk a few words about the Nanjappa sir, please feel free to come.
I'm volunteering because I should tell you that, you young, some of the young faculty don't know. And Ramki and I, when we joined within a year, Professor Krishnamurthy made me in charge of attenders. You remember, right? And I should say, what PKD and Ramki said. I think at that time we had 7 or 8 attenders, right? So I used to allot spaces and jobs, and I was a faculty, I was not office staff. But we did, right? But the interesting thing, the reason we did is because we wanted to do things, right? So, and I can tell you, Nanjappa and Arunambi is somebody, once if you assign in the morning and leave it, and it'll be done. You don't have to worry about it. There are another 6, and Ramki knows I used to roam around at 12 o'clock in the afternoon searching for these guys. Some of them won't be even in the department. But anyway, that's a history. But, he is an example of, irrespective of the profession you're in, the commitment and sincerity to the job, punctuality to the job. He was always on time, and he was in charge of our lab at some point. I never had to ask him for anything. Things will get done automatically. And I think that he's a role model for any profession, for punctuality, honesty, sincerity. And, the department success, I always tell them, people like him are the pillars in the background for the success of research group, success of the department. So I want to thank you, Nanjappa, for your commitment. I think you've done a wonderful job. Madam too. Yeah, thank you for supporting him, in spite of all the quarrels, of course, which is normal everywhere. Thank you very much. Thank you.
I think we are following some kind of seniority order. Arunan, of course, let me make it public. Arunan is my junior in the institute. Nanjappa, as my colleagues already pointed out, is one of the 2 pillars of IPC, the other being Arulnambi. I've had the fortune of having Nanjappa for our lab at least twice, I think, in the old building. And as my colleagues already pointed out, he has a lot of dedication to what he does, sincerity and honesty. And I also had the opportunity to work with him in the library, in the IPC sub-library, after Loknathan, superannuated. So he took care of the library, you know, uh, yeah, from 2016 onwards, and he maintained the records meticulously. And of course, from time to time, he was bringing the list of students and faculty who were defaulters. And I said, go and approach them softly and then try to recover. At the end of the day, our job is to make sure that the library is well maintained, which he did quite well. The other aspect that I had quite a bit of interaction with Nanjappa was the time when I had to take care of the major project, which is the Chemical Sciences building in terms of the lab infrastructure project. So I was quote unquote appointed as the chair or coordinator of the project execution group, and Nanjappa was appointed here or deposited here, let me put it that way. So we had to interface, I had to interface with him quite a large number, many times. And as Pushpendu already pointed out, he was quite exceptional in terms of picking out the right key without any hesitation. So I found him to be, really smart in that regard. So Nanjappa also, one thing that struck me by observing Nanjappa was that he never said no, as my colleagues also pointed out. Whatever task he was assigned to finish, he used to complete, and then the rest is all taken care of. So thank you, Nanjappa. We are really grateful to you for the wonderful services that you have provided to this department and to the institute. And thank you, madam, for all the support that you have rendered him. So I wish you both and your family really very healthy and long life. Thank you.
Now I would like to answer.
Hello, everyone. I've not been here much less for much fewer years than the other people who spoke before me, but I have also interacted a fair amount with Ms. Nanjappa. Well, I'm a theorist, but how would a theorist interact with staff who are typically to help with the experimental labs? Well, there were lots of purchases to make. There were things to oversee. And I've been interacting with him since the old building. But especially in the last 5 years, as people have been mentioning, when coming to new building, I had a task here as well, which was the network. And that was somewhere in between Vivek and Bhadra starting in this lab and the department moving in. And I have really relied on his availability in the building to be able to coordinate between him and the network people. There were teams of people doing the work with the passive cable laying to the switch setup, everything. So all of this, the network people came to the building first. So we've been seeing this building from inside out for quite some time. And without Mr. Nanjappa, the work could not have happened. Because he was available all the time, it was possible to interface with the network people in a very smooth way and get the work done. And so I thank you very much, Mr. Nanjappa, for all the help from the old building until here. And as was already mentioned, IPC will sorely miss you. Thank you very much. Yeah.
Now I would like to invite Nanjappa sir for speaking a few words.
Good afternoon, everyone. Sorry that I do not have any experience of stage talk. Firstly, I joined in 1986. At that time, Professor V. Krishnan was the chairman. So the first day when I came to report to the department, as usual, I was well dressed and stood in front of Professor V. Krishnan. He asked me, "Will you work?" I was appointed as a laboratory helper. "Will you work?" My language was very rough. "So if you want, you see, sir." So after completion of 2 years, that was the probationary period. So all my colleagues, that confirmation order came, but mine I didn't get. Suddenly I rushed to Professor V. Krishnan. I told that, "So this is what happened. I was doing something, don't do anything, immediately rush to the U1B and find out what has happened." So I went to the 1B section. My name was missed. I told and I came and told Professor V. Krishnan, so much that affection we had. Thank you very much, sir. So initially 1986 to till today I worked in IPC. That is 38 years. I joined campus in 1983, almost 41 years. I worked in the aerospace department. So in this period, I have seen so many faculty members, about 30 to 40 faculty and 30 around 25 supporting staffs and hundreds of students. I heartily thankful to everyone, those who have associated with me. Thank you very much.
Thank you, Nanjappa sir, for all the services you have done for the Chemical Sciences Division. Thank you, ma'am.
Now we are starting the felicitation session for Professor Umapathy. I would like to invite Professor Umapathy to the stage.
Now I would like to invite Professor Arunan sir for the stage, for the felicitation.
No, I don't. I won't come for all of these.
I invite Uba ma'am to the stage. Now I would like to invite Professor Ramakrishnan and Professor Chinmay Ranjan to give the T-shirt to Professor Umapathy sir.
So now you all know why I just wanted to give a lecture and go. This is something. So you want to say?
Back side is more.
See, No, this photo, we were together in Hebrew University. We were walking around the shopping area. There was a guy trying to sell this to us. I said, I don't want it. He said, no, sir, you wear it. So he put it on me, and then he took a picture. And then we returned it back to him. So this is the history of it. What does it say? Oh my God, it's so much. Oh, brilliant. Thank you very much.
Yeah.
Excellent. Oh, hello, Habibi.
Moving on to the felicitation talk, I would like to invite Arunan sir to the stage.
So, in fact, I joined the department end of May 1997. That year, Mr. K.C. Patil was retiring. The chairman was K. Kishore. He was not here, so he asked me to arrange the felicitation function for K.C. Patil. From that year, we have been doing this, getting a shawl and bouquet. And Umapathy used to say, we should not give bouquet, why don't we give a t-shirt? So, in the last few years, we started giving a t-shirt. Then our office, in fact, I should thank our office staff. I said, why are we giving bouquet? Let's give a plant. So, we are slowly improving. Hopefully, when some of us retire. Let me just say a few words about Professor Umapathy. I joined the department on May 29th. I think Sampath came 5-6 weeks later. Because we were young, but not as young as many others. We were somewhat old at that time as well. I was in Kanpur for 3 years and Sampath was in Japan, so we joined a little late. But of course, we are new to the department. I remember Umapathy was one of the few who had a car. I bought a big TV, so I called him, can you help me take this TV? He had this Maruti van. It's no longer in service. He had a trunk that was big enough to put the TV. So those days, as Umapathy mentioned, we used to do a lot of things together. We used to go to MG Road and buy the silver plaque. The Barton Center, I think Professor Vasudevan was mentioning, to stop all of things. So we used to go there, and of course, you don't go to MG Road, just buy a silver plaque and come back, isn't it? So we had many other things to do at the time. Whenever we had a new faculty potential candidate, I'm just telling this because this is something as young assistant professors, Umapathy, Ramakrishnan, Sampath, and they all were doing it. We used to take them out for dinner one evening, spend some time. So it's important to make the candidate comfortable, and Umapathy was very particular about it. So we had done a lot of work. As I told you, the second or third year I was here, he won the Swarna Jayanthi award. The time it started and it's continuing, and I hope it will continue now, because this 31st July, he won't have the responsibility as a faculty here, but he'll have everything else. He can really dedicate his time to research and his startup. So one thing that's India has not been very good in general is to encourage faculty to get into business. Somehow our attitude has been to keep Lakshmi and Saraswati separate. I don't know why that attitude is there. Umapathy is one of the few who ventured out. He was trying to tell you the difficulty, but I don't think many of you would have understood that. So I have seen that. Because it's easy to do research and publish papers, which almost all of us do. To start a company and sustain it is not easy. So he has really worked hard on these things. I have told one of these things to the experiment that he did, femtosecond coherent Raman. He was the second or third in the world to do. I know several in the US who tried, but they could not succeed. Umapathy could do it in Bangalore here. My only regret is I don't think he regrets this. I wish he was just focusing on that and doing, but he wanted to help India more. So it would have been good for him to continue that because I don't know how many can do that kind of experiments here. One good thing about our department is this spectroscopy and in fact gas, liquid and solids and different kind of spectroscopy, IR, Raman, UV and microwave. So our department got a lot of attention. I had told him this before, only this femtosecond coherent Raman. Of course, resonance Raman itself was not possible. In fact, he was the first to do that in India as well. Until that time, several had tried but could not do that. And femtosecond coherent Raman is still a remarkable achievement. Many would not understand this. Only those who are in the field can know this. Because as he pointed out, he has more than 10 patents, more than 200 publications, but none of this would reflect the difficulties he had gone through. To do experiments like that was not possible. In the time we have been encouraging that whenever we hire faculty, also I keep telling them, you should do something unique that no other department, not only in India, but anywhere in the world can do that. So that way, Professor Umapathy has been a real pillar of strength in our department because he started in 1990, as I told you, as a lecturer. Those days is very different. Usually after 3-year postdoc experience, he can be appointed as assistant professor. Yesterday I was talking to Professor Krishnan, I still don't understand why. He said, Ramakrishnan and Umapathy were appointed as lecturer. I don't know why. And a few years later, they became assistant professors. I'm sure the faculty here know what COP means, Committee of Professors. They take care of everything in the department. But Umapathy was saying, he said, we shouldn't wait for that. We had a CAP, Committee of Assistant Professors. So we thought we will just do things the way we want. So it used to be called CAP at that time, Committee of Assistant Professors. In fact, when he joined, of course, when he joined, they had an empty lab. When Sampath and I joined, the situation was still similar. We didn't have an office or lab, but I had kept my spectrometer in the corridor and put 2 doors on both sides. Sampath was sitting without an office for many years. But we all realize this is not helpful, not just to the young faculty who are hired, but to the department and institute. Because if we are hiring a faculty, it's in our interest to help them. This change started when Professor Mukesh joined our department. Like Professor Mukesh speak on this occasion as well, both about Nanjappa and Professor Umapathy. And his son became one more victim for dengue. So he got the message just when he was here and he sent me and left. Yesterday I was in the health center, there were like 20-30 reports. I just wanted a HP1AC report. They said that can wait. All the dengue reports have come. Anyway, I'm digressing. So at that time, we were very particular that the young faculty who joined, this is all we decided, and when Professor Mukesh joined, we had a lab, office, and a student waiting before he joined. And you can see the difference it makes. Since that time, we have done this for most of the new recruitments. I hope that will continue after we. Because if you ask people like me and Umapathy to speak, we'll talk about all the difficulty we had. I hope that was the past. We tried to make a change, and Umapathy played a significant role in this. I hope our younger faculty will continue this and ensure that the new faculty who are hired can launch immediately without any break. I would really like to thank Professor Umapathy for his very long service. It's 1990 and now we are in 2024, 34 years. And of course, he'll be here for 5 and many more years. I think now he can really focus on research, and I already told him in case you get money, just do the business. Because very few are willing to do that. We can go on doing science and publishing paper, that is not enough. In the West, that has been possible. You can start a company and still continue as a faculty. Somehow we have not been encouraging that. I hope that will also change so that our younger faculty can do both very well. Thank you very much, Ma.
Now, I would like to invite Professor Binni sir for the felicitation talk.
Good evening. It was just last year that I was here being felicitated for my retirement, along with Professor Das and Professor Netaji. And on that occasion, we had a party outside the institute where Professor R.K. had written 2 poems for us, for Pushpendu and me. And just a few days ago, he wrote another poem, this time for Uma, at a party that we had to celebrate his retirement. And I thought that it would be a black mark on my name if, as the former editor of the departmental magazine, I didn't also contribute a poem on Uma's retirement. So that's what I've done. Over the weekend, I put together something which I'll read out. It's very much along the lines of the poems that R.K. wrote. It's just light verse. But the title is somewhat different. Professor R.K.'s title for Uma's poem was Uma the Enigma. And I thought the title wasn't entirely appropriate because Uma, to me, has never seemed particularly enigmatic or mysterious. I think he's someone who's never made a secret of the kind of person he is. He's always been very forthright, very frank, no equivocation, no subterfuges, nothing of that kind. So the poem that I wrote has a different title. It's called The Man with a Plan. And here it is in iambic tetrameter. When first I beheld him in the old IPC, he was a pipe-smoking Briton of high pedigree. All suited and booted, he was fashionably smart, and he'd clearly decided he was someone apart. His bearing was regal, his speech upper class, and I thought to myself, a real pompous ass. But I soon changed my mind after knowing him better. He wasn't a toff, just a dashing go-getter. And though different from me in every which way, we became coffee companions at the start of each day. The practice continued till that one fateful call lured my fellow imbiber to Aizer Bhopal, where he shook the place up in true Uma style and left a mark there that will last a long while. Now back in our city, he won't stop for a rest till he's built a new scanner that can vie with the best. He's practically there. His startup is humming. I have a strong feeling an IPO is coming. So Uma, my friend, if those coffees meant something, you'll give me some shares and you'll give them for nothing. In fact, you could make me a part of your outfit since it'll need a new name and I could provide it. I bet that together we could put up a show and retire at last with a huge pile of dough. And with that parting thought, I'll call it a day and wish you the best and a hip hip hooray. Thanks.
Thank you, sir. Next, I invite Professor Ramakrishnan to the stage for the felicitation speech.
So I just have a collection of photographs that I thought I will have it playing while I say something. So so I sort of mumbled in Binny's ear, Binny, you think I should read the poem? And he said, I'm going to read a poem. And I said, oh my God, then I'm not going to read the poem because I know Binny does a fantastic job just as he did. He had a lovely poem. So I think, yeah, you can just play it. So as I speak, you can watch some of the old pictures that we had from my archives. I could only pull a few out in the small amount of time that I had. So as Binny reflected, Uma is not an enigma, but I was trying to rhyme, Binny, for what a better. So, but Uma does have a lot of hidden talent. In the sense that he reveals himself in layers. It's not that he hides, but he reveals himself in layers. And I think I have continuously learned about Uma over a very long period of time. And there are many things that I recall very fondly. Yes, I do remember his pipe smoking gait along the corridor. Those were days where smoking was not prohibited, and you could smoke away pipes. And Uma came in with a suit, actually, the first day. So it was quite a surprise in IISc. People don't walk in with suit and pipe. So, yeah. So, Uma was, as he said, a classic Brit sort of appearance he had, and also accent. After he joined IISc, the first thing, just like Balaji made it a point to sort of assert his seniority over Arunan, I must assert my seniority over Umapathy, because I joined about 3 months before he did, and Binny joined in the same year early. So we were some in the same year. So Binny joined in January, I think, and I joined in early September, and Uma joined in December. So we were 3 in the same, and I might have said this, but we did form Umapathy's initiative. He actually coined a term called Binu Mark, Binny, Uma, and RK. So there was a company that we floated, which never went anywhere. Uma, maybe that's what you should do now. So, as Binny said, those were days when there was a lot of camaradereship in IISc, and one of the reasons it really blossomed and brought people of different generations together. Of course, the younger people used to go, but Uma had a knack with people, and he still does. And he's somebody who befriends people very quickly. And this is a skill that I have learned about him as I watched him function. I know my friends who became far better friends with Uma than me. When they come here, they only call Uma. I mean, I introduced him to Uma, and now the guy doesn't call me, he calls Uma. So this is characteristic of Uma. He really befriends people very well. Somebody who, he has that incredible skill. So he used these charms to actually bring the senior people to join us for the tea visits that we had. And also not only tea visits, other liquids as well. So it's quite surprising that Uma managed to get Chandra to join us. I mean, I don't know, A.K. Chandra was one of them who wrote the book on quantum mechanics, who was a senior colleague of ours. And he managed to get him one day, and we went out and had a beer. So him, of course, Professor Krishnamurthy. And Krishnan doesn't need too much prodding. He would join us anyway. But Krishnamurthy did, and I think Uma succeeded with Krishnamurthy as well. So, I think, I often say that when you grow together facing difficulties, right, the bonding is actually much stronger. And I used to tell people that when you sort of, when you have to engage and sort of really fight with systems and things to get things done, and when you do it together, there is some amount of sharing of these difficulties that and mutual sympathies and appreciations of these that bond together. I still recall, even though both of us work in very different areas, when we wrote papers, actually we shared it with each other, even though just for us to read. We'll send it, hey, this is a draft, check it out, what do you think? He would send it, and likewise I would do it. It was areas were completely different, but that's the way we work. We just send it and say, hey, tell me if there's anything, any inputs you need, what do you think, is it written well? That kind of thing. And so there's a lot of things on those early days, and I think Uma's, as he showed in his talk, Uma is an extremely dynamic, extremely positive, and extremely optimistic. Okay, and these are very rare characteristics that enables him to take risks, and risks of the kind that I haven't taken, and many of us will not. The fact that he has sort of transitioned, as Pushpendu said, no, Arunan said he would have preferred he had stayed in ultrafast Raman spectroscopy. But that's Uma. Uma just likes to move and likes to take up different challenges. And you can see the variety of things that he has done in his career. That tells you his ability to translate, ability to move from one discipline to another, not knowing anything in biology. I think, Uma, not knowing pretty much anything. I still don't know any biology, but you have picked up so much. I mean, the fact is that, you just get into an area very confident that you will pick it up as time goes along, and you will develop the required expertise to crack problems. That is Uma, and you can see that he had no idea of biology, but then he chatted with people across the departments, across divisions, across institutions, hospitals, and just got moving. And his students moved along. This is his skill, to get people. I mean, if somebody is coming to work with me and I don't know biology, and I'm telling my student, I want you to work on this, the fellow will look at me and say, look, you don't know this. Why are you getting me into this? But that's his skill, right? He managed to convince his students that these are problems that are worthy of solving and that you can solve them. You can solve them, and we will learn together, That's this idea. And I think that really is something that he has done remarkably well, moving from one area to another, biology to checking this. And now he's telling me he's just said that, right? In a few months, you will see his machine in airport. I mean, look at the confidence, right? That's what is remarkable. I mean, this is what he does. I mean, this kind of sort of go-getter is a term that Binny used, and that's exactly what he is. He hones in on a target. This is what I want to do, and he does it. And so, he's been a great friend, and we've done many things together. Some of you might have seen. I think, thanks to Uma, I'm on the wake. He's sort of moving along, and Uma, sometimes I'm in the wake, just being pushed by the movement of the water as the ship goes along. So, he was the captain of the Indian Institute of Science faculty team, cricket team. When he joined, he was the captain, and I have played cricket, never got selected anywhere, leave alone even my class team. So I was no good in cricket. But he managed to get me to play cricket. So I went there, and I think by mistake I caught a good catch, and people were quite surprised. So Ron ran along and I caught it. I said, wow, this is pretty good. Maybe I could have been better. But that's Uma. He was an excellent wicketkeeper. He's played with people who have played for the New Zealand team. So when he was a PhD student in New Zealand, he actually used to play cricket. And some of the people whom he has played with have played for the New Zealand cricket team. So you can see he has faced fast bowlers of the type who bowl to the best in the world, right? And he was their wicketkeeper. So he's the wicketkeeper captain of our institute faculty team. He's won medals, he's won cups. I think there was some competition where he won a cup in Mysore. I didn't go for the serious ones. I was only here just hanging around when he played. So that's one thing where I got sort of swept away by the wake. The other thing is his desire to perform skits. And so one of these days for the Alchemist Club, he said, Uma, hey, come here, let's do something. I said, what? So he said, let's play a skit. And I said, okay, we can give it a shot. So that started us on, and I think we did a few of them. And it was reasonably popular, but I think once he became very busy and unable, and our script writer also was unwilling to do. He's sitting there, Binny Cherriel, he's a script writer, and so that's the only real collaboration Binu Mark has had. That's the skits that we performed on these days. So anyway, lots of lovely memories, and some of them are showing up on the I just can't believe this day would have come so fast. It appears just, a few years ago that we joined. We don't mentally age. It's a strange thing, even though we physically age. I shouldn't be doing this, but you see, my mind is telling me I can, but my body probably can't. But so things have moved so fast, and it's amazing that I'm standing here saying all this on Uma's retirement, and I'll soon follow Uma. So keep a space for me in your company. I think I like that guy. So I don't know what Benny is going to do, but I can certainly help. Anyway, all right. So thanks a lot. It was a wonderful opportunity. Thank you, Uma, for the great friendship. And I think we will cherish it. We'll continue. We have lots of plans which we'll do. All right. Okay, thank you all, and thanks for the opportunity.
Now, I would like to invite Professor Balaji Jagirda, sir, onto the stage.
All right, anyway, while that is being taken care of, my colleagues already touched upon many aspects of Uma. I'll touch upon only a couple of things, maybe a couple of anecdotes actually. Yeah, when I joined the institute many years ago, I came to know about Uma, met him, and I found him to be a very energetic, enthusiastic young man with full of something to, as RK already pointed out and Binny also pointed out, a go-getter of sorts. And of course, he's a real go-getter of sorts. I have had interaction with Uma on many instances. I'll not go through all of those, but I think, like myself, I'm sure many of those who have had an interaction or known Uma, he has a big influence on people. Okay, I'll just mention one influence that he had on one of our colleagues in the past. I'll not name the person. I'm sure my colleagues will know that, know him. So in one of the felicitation functions, the person who was felicitating a superannuating staff member, he mentioned that, instead of memento, he said, I would like to present a memo. So Uma wanted to, we always was fascinated by this word, quote unquote, memo. Such an influence he had on our senior colleague that instead of saying memento, he said memo. So the entire, lecture hall burst into laughter. Uma, because of Uma, I've had the opportunity, RK touched upon cricket. So when I joined the institute, I was a cricket player. I played for under 15 inter-school tournament. So when I joined the institute, I came to know that Uma used to be a wicket-keeper and a wicket-keeper batsman. Because of him, I met some of the cricket players of the IISc team. And then I think Uma used to mention that I met them. One of them is Simha, and another fast bowler. I don't remember his Chanakya. He used to tell, I mean, Uma used to tell me that, they bowl so fast and it's really difficult to keep the wickets. Some of his friends who played cricket with him, we had an opportunity to bring them to the department. They are colleagues in other departments. So we used to have these faculty members from other departments come and give seminars, Wednesday seminars in our department. So we had that practice for a number of years. I think it is, I don't know, now we don't have slots. That's a limitation. So we used to call young faculty members who just joined the institute to come and talk about their own research. So I met quite a few of them, and then they are always, whenever I meet them in the absence of Uma, they said, "Oh, okay, Uma." I'll also tell you another thing that has happened in the recent past. When I was in the UG office, I reached out to Uma for a small help with regard to getting the institute on board for the ICER aptitude test mode of entry when KVPY was scrapped. And Uma was very supportive on that count. So one of the modes of entry for the undergraduate program for the students is KVPY program, and this all of you know that KVPY program was scrapped, and then ICER, all the ICERs together formed a consortium and conduct a test. Through that mode of entry, ICERs accept students for admission to the UG program. So we decided to have the institute also admit students through ICER aptitude test. And Uma, it's always good to have friends in high places, and so thankfully Uma was in ICER Bhopal as a director. I reached out to Uma and then asking for help to have the directors, which is the Joint Admissions Committee. No. This is it JSC? I think JSC. So he was able to convince all the directors. Although they very well knew that the top students come to IISc and they lose out. Despite that, he was able to convince all the directors of ICERs, and we are on board on the ICER aptitude test mode of entry. And last year we have had the first set of students come to the institute. It was 1 to 30 we offered, 1 to 29 joined. The rest is history. I think this year also it's going to continue the same. I'm not sure if Uma was able to succeed in making Bini eat curd rice in the last 34 years of his stay here. I hope he's going to continue his efforts to make Bini eat curd rice. So with those remarks, Uma, wish you all the very best. Thanks for the wonderful friendship that we have had, enjoyed, and will continue to do that. I think last year, RK started one group, 26ers. I have been inducted into this group as an honorary member. So I hope I will be continuing to be with that group. Thank you very much.
Now I would like to invite Dr. Sri Vidya, who is a former PhD student in Professor Umapathy's group, to the stage.
A very good evening, and I thank the IPC department to call me back. Thank you, Rupa, for reaching out to me. It is not even in my wildest dreams that I will stand here on his felicitation and speak about the experiences. To give a glimpse, everyone's PhD life goes with usual ups and downs. That's something usual. But once you're done with your PhD, and you start thinking what you're going to do next, I made up my mind that I will not go into academics, and I'll go into industry jobs. He tried pushing me hard to go into academics, but he couldn't succeed. And when I was about to start looking for the job, the COVID hit. The terrible time I started looking for a job, Then I started going into the forums of career things and many things. And once I came up, I was in a YouTube online session of India Bioscience, where they spoke about alternative career options. And one was grants management, which I have never heard in my lifetime in the research, something called grants management. So I was hearing it is from the bio field of it, and they were telling how a grants manager would be helpful in a research environment. When the grants manager from the funding agency side and from the academic side, when they were speaking, one thing I felt, one thing I started realizing was most of the part of grants management was something I have done it during my PhD training, which I had no realization during my process of PhD, because he asks me to do these UCs and SCs, which I cribbed about while doing PhD, but still, some amount of time that I dedicated to write proposals and to go behind these UCs, SE reports, get the sanctions. These were something very helpful for me to start a career, so-called grants manager. And that came to me with a surprise when I reached out to these panel members offline, and they told there's an opening in IISc in Office of Research Grants, which I never knew that existed in IISc when I passed out. And when I applied for the job and I get shortlisted, it was an online Teams meeting with 7 of the deans present there. It was a nightmare. It was like giving another PhD interview there. And I think Professor P.K. Das was also one of the deans present. And one question I very vividly remember is, they asked, what is the percentage of work that you put in a proposal? My answer was not a straight answer like 20%, 40%. I said it was gradually increasing as year goes. In the year 1, I gave an input of 10 to 20%, and when I came to year 5 or 6, it was almost 80 to 90%. That is something which came out of my own experience. This question I was not completely prepared of, because grants management interview, I have no clue what the questions are going to be. And with deans of all the divisions on the panel, it was something, it was a satisfaction after the interview, though I get a job, I don't get a job. But I was happy internally that I could actually convince the panel that I am capable of this job. And thanks to you for that training during my research career. So I ended up in a grants manager at IISc in 2020. And in 6 months of time frame there, as a part of the work, I started helping the IISc's Quantum Tech initiative to formulate various things. And quickly they told that we need a full-time technology manager or a coordinator for the whole project. And after 6 to 8 months of stint as a grants manager, I moved as a technology manager for IISc's Quantum Tech initiative. And that's been a great learning experience. We never knew what life would give. You would be planning for an academic career or a postdoc career, but it was complete surprise that I could end up in a research management career, and still it's fascinating. And the most fascinating things were many things which I've observed from him as a research environment, I still put it in practice as a research manager. Few of the things that I have learned from him are not to micromanage things. After first year or 2, once he knows that you're going to get the job done, he has never micromanaged people. He used to tell this is the direction that you need to go, and he has let us free to do whatever we want. And the thing that he always insists to trust the colleagues. That helps me today a lot. And he always tells you have to trust your colleagues and teammates. And he has always believed in us to experiment any new things. We have argued with him. We have fought with him. Sometimes I have wrong, sometimes he is wrong. We have agreed and we have moved on. So that healthy environment I always cherish. And he was always a great listener. He never bothered whether a first-year student is giving a suggestion or a 12th standard student is giving a suggestion. We had varied people coming to our group. Even an 8th standard student have come to us to do an internship. And it was all a learning experience to be a part of such big interdisciplinary group. In fact, that was the one which helped us to crack the single bacterial spectroscopy, which was initiated from us. And I think we were one of the first one to do in India, and one of the top 2 to 3 groups in the world when we cracked to identify single bacteria and differentiate them. And with taking the support of all the Umapathians, we thank you so much for whatever you have given us, and it has been a great journey for all of us. And I'm sure everybody would agree is we are in different places, and most is because of your values that you have inculcated. Many thanks to you. Thank you so much.
Now, I would like to invite Dr. Vinay Kumar, former project assistant in Professor Umapathy sir's group, to the stage.
Hi, good evening, everyone. So I'm going to keep it very raw. As such, I don't have a structured talk. So to begin with, I was a guy who really was careless, a lot careless in life until I joined Professor Umapathy's lab, where everything started falling in place. The very good part, or the fantastic part about this man is his willingness to give opportunities, right? Many of us do have great minds, some of us don't. Some of us who do not have great minds, we need an opportunity to learn from great minds like yourselves, right? And this man always provided that opportunity to anyone who came by. And, I've seen many guys. I'm just one example. There have been many people who've come by. I don't like to name the region as such. There was one person who came by with zero communication skills, right? And he was given an opportunity to work in the lab, to learn from the others, from the great minds. And this is something that not many do, and these are opportunities that all of us really want. Many of us out there are looking for these opportunities to learn, and we only need this little opportunity, and Professor Umapathy always provided that, and we are absolutely grateful to you, sir. Whatever I am personally right now in the professional space is mostly because of your support and your incredible patience with us, with all of us. And yes, I personally wish you, and as a part of the project assistants who work with you and the JRFs, I think I speak for everyone. Thank you very much for your support, and we wish you the very best with your startup and all your beautiful journeys ahead. Thank you so much, sir. Thank you, everyone.
Now I invite Ms. Rekha PT to the stage for the felicitation speech.
Good afternoon. So on this occasion of Professor Umapathy's retirement, we would like to express our gratitude towards our supervisor. And although mentioning all of the things that we are thankful to him will take much more than a few moments, I'll try to stick to a few of them. Thank you, sir, for guiding each of us distinctly, understanding our unique strengths, and tailoring your mentorship to fit us. For teaching us how to turn complex concepts into interesting applications, and also for the instant set-it-ups, responses that we always got whenever we go to him and tell him, sir, we want to show you some data. On the spot, we'll get the response, set up the projector. That's what we have always got, even though he would have been very tired. So while you were the director at IISc Bhopal, you traveled back and forth from Bangalore every other week. But even after those long travels, you were always ready for a chat. And we would like to thank you for the numerous questions, relentless questions in the group meeting that always challenged us and made us think deeper, and also made ourselves defend our ideas very confidently. Our lab groups were always very big and diverse. So your insistence that we speak English and make a PowerPoint out of every new topic that we come across made us very confident speakers. We cherish the long coffee sessions that follow our group meetings where we discuss everything from science to politics. We can never have enough of that. I would also like to thank Sir for allowing us the freedom to find our own paths while always gently guiding us whenever we needed it. Uh, for encouraging us to dismantle our own instruments and understand how they work, and for making us fearless problem solvers, for teaching us to make decisions boldly without the fear of judgment, and for teaching us to have a positive outlook, and for reminding us that it's okay not to know everything, and showing us how to truly enjoy what we do. Thank you, sir, for being our supervisor, mentor, and our supporter. Of course, thank you for surviving 32 PhDs. We look forward to the continued journey we will share and the remarkable achievements that are yet to come. Thank you, sir. Thank you.
If someone wants to talk a few words, please, Chinmay sir.
So thank you, Professor Umapathy, for all you have done. All you have done. So one thing I noticed today is I got up from the stage from that side, and Professor Umapathy and Professor RK came from here. Yeah, and that tells about the kind of energy they have. Yes, right now, and he's not a person who is winding down. He's a person who is winding up to launch. Yes, you can feel that. And that's the great energy I think he imparts to everything he does. I mean, compared to all of senior faculties who enjoyed so much time with him, I had relatively less exposure to him, but it was an immense opportunity to learn. So he was the chairman who hired me, and he initially advised me, and he helped me negotiate prices of equipment. Yes, and he also helped us organize a conference. We were basically following his whatever he said. And during this entire thing, it was wonderful to watch him. I mean, he's like a master tactician. Yes. And one thing I'll tell you is when the negotiations meetings happen, you can see immediately the moment he sits there and speaks, the gravity of the room shifts, yes, towards him. And that's the respect he immediately commands. And it was just so effective, yes. And his negotiations, I have never seen somebody negotiate with that, people with 30% discount. I mean, he's just somebody who is just able to do that, okay. So if somebody tells you that you need to lose your ego and, learn from somebody from IIM, please ask them to shut up. You are already up there, way above in ability compared to those people. And many things I learned. One is the general positivity. I think whenever I have gone to him and asked for him, he's open with advice, he's open with help, yes. And that's his general nature, I think. Because of this, he has made friends all over the place, yes. And because of that, he's someone who sees things much more broadly, yes, and can make the connections very quickly. So even if you think you are lost, he's somebody who sees a bigger picture. He knows where the things are and how the dots connect. So he's somebody who can guide you, especially young people, to do that. Yes. And if you notice the slides, yes, Professor Umapathy was presenting. You could see one thing. Yes, it's a moving theme. It starts somewhere, it ends somewhere, and there are straight points and beautiful colors. Yes. So it's straight talk and colorfulness. I think that's what characterizes his. To me, that's what characterizes his life. It's very colorful. He enjoys it. Yes. Everything he does, he really enjoys it, and that's basically rubs off people who are working with him. Yes. And even the short time I had to enjoy with him, I really enjoyed. I really learned a lot. Yes. And so that is something I think all especially young people, you should note. Yes. I mean, he's really successful, and you should understand why he's successful. It's not easy to nail it down, but it's a part of his personality, and it's not just the science. It's outside of science how he conducts himself, yes, and how helpful he is to everyone, yes. And one thing I noticed with him is he's extremely decisive. Like, and Rekha somehow summarized certain things very quickly, yes, is he takes decisions and says, okay, even if you don't know everything, yes, you can still take a decision. Yes, and I think that is something that characterizes him a lot because that allows him to move faster. Yes, he can decide fast and move to the next step. And you realize people who sit and think about pros and cons too much, they sometimes stop moving. Yes. On the other hand, who move and decisive, yes, they make the world converge around them because they carry so much momentum inside themselves that you kind of tend to go around them. Yes, and he's one of those people. So he has his own center of gravity and he moves around and things move around him. Okay, so I really wish him all the success for the next stage of his career, and he has been a source of inspiration and has taught us. Thank you, sir.
Now I would like to invite Professor Umapathy sir to the stage for speaking a few words. I'm sorry. Sai sir, please come to the stage.
Go up this way to say I'm still young. Well, I joined this department about 13ish years ago. Upendra and I joined around about the same time, and we had the benefit of wonderful interactions with Umapathy. I'd like to think he was fond of both of us, both Upendra and me. He's not here just now, but I think he would have said the same. I've had, lots of interesting discussions with him over time, and he's also given me a lot of wonderful advice as well over the course of the years. Especially at times when things were not going too well, he was patient. He listened and advised well. Don't know if I've followed the advice so much, but he was the key thing was that he always had a patient ear, and he was always smiling. He would always have as you know, I mentioned, the positive attitude was something that rubs off on you. If he had a problem, you would not hesitate to go and talk to him about it, and you could be vulnerable around him, and it would be fine. And that really helped. That really helped to sort of find one's own bearing and try to move forward. So so thank you very much, Professor Umapathy, for your wonderful words of advice and suggestions, and all the very best for the future. Thank you.
I invite Professor Umapathy to the stage for speaking a few words.
Right, so I think all of you have been sitting for too long. It's time to go home. So just wanted to take the opportunity to thank the department for organizing this. I'm not, I'm not for such things. PKD knows and everybody knows. I don't like to be in the limelight. I avoid as much as possible. And I try to, even if you're on my Facebook, you will see that I don't put anything that is popular or make it pure important and all that. Because, I think that I felt that right from my young days, making someone important is what makes the system collapse. Because then other people start aspiring for it and then it gets complicated. So I always said, everyone has a position, we all have a role to play. Even in IISc Bhopal, when I was a director, I always tell them that ignore me, don't even look at me. I'm doing my job, you do your job. You're a dean and I'm a director, so how does it matter? When for example, in my first year when I was there, I can't even go for coffee. I mean, it was so difficult. I go sit there, then 5-10 guys come around and say, sir, this, that. So I used to tell them, no, all of you run away. I don't want any of you here, And if I go to the auditorium, some students having some dance party, something going on, drama, I love to be with them. So I try to go. Once if I go, they say, come as a chief guest, sir, you give gifts and all. I tell them, no, I'm sitting in the back. don't even, notice that I'm here. So after about a year or so, I got them convinced that director doesn't matter. It's not anything. So the same thing with our decision making and anything, because once if you know what the question is and you know the pros and cons, if the cons are smaller than the pros, take the risk and make the decision. That has been my policy. If I don't have a chance of winning a game, I always tell even my own son that, when you get into a confrontation or when you have to make a decision, you quickly analyze to see whether you have 60 to 70% chance of succeeding. If you have a 70% chance of succeeding, go for it. Go fight out. Right? If you think there is only 50% or 40% chance of succeeding, just give up and move to the next. So there's no point in trying to analyze too much. And so that has been my policy. So I enjoyed my time from Professor Krishna's time. We were a great, those were the days. I miss those days of going out, spending time. And I have to say, Ramki and I were these two little young boys who are extremely naughty in the department. Professor Krishnamurthy was chairman, Professor Krishnan was divisional chairman, and there was a lot of senior professors in the department. They never looked at us as a problem. They actually looked at us saying, these troublemakers, fellows always want to do something. But they never disagreed with anything we said. We said we want to fix this room, we want to put internet, we want to get computers. They said, yeah, okay, if we can get it done. And that continued, and that kind of support that I always enjoyed. And so I want to thank all of you for all the support and for the opportunity. And I'll be around and we'll keep meeting. And just that I won't be formally coming for meetings. Otherwise, informally, I'm always available. Thank you very much.
Thank you, sir, for being such a great inspiration to all of us. Thank you, everyone, for joining. There's a high tea organized at the ground floor. Have a nice evening.